Cool. And so I'm going to pick up where I left off on the fractions practice worksheet and talk a little bit about reducing fractions to lowest terms. So when we're multiplying or dividing fractions, just to recap, we do not need a common denominator. The time when I need to get a common denominator is whenever I'm adding or subtracting. When we're multiplying or dividing fractions, often we're asked to get things to lowest terms. One of the ways that we can do that is by factoring all of the numbers and finding any ratios that are equal to 1. So if I look at 12 times 7 over 14, it's totally fine if you look at the 7 and the 14 and you're like, oh, well, 7 is 2 times 14. I'm going to cross those out and write a little 2 down here. Totally fine. If you are struggling with kind of how to get started, my suggestion is to think about breaking all the numbers down into their smaller multiples. So 14, I can write as 2 times 7. And now on the top, I know I'm going to have a 7. So if I think about the 12 as 6 times 2, then that 2 over 2 becomes a 1. And that 7 over 7 becomes a 1. And my final answer I'm left with is 6. You don't have to show me any work. If this is a problem and you look at that and you're just going to do it in your head, totally fine. As long as you're getting them right, I don't need to see any work on this. If you are just feeling it out, do a little bit of work. So if I'm looking at 5 times 6 over 20, I could totally think about that as, well, if I look at the 5 and the 20, 5 goes into 24 times. I'm going to write a 4 on the bottom. But if there's any level of hesitation there, again, I would take a moment to write that 20 as 5 times 4. Now that 5 over 5 is equal to 1. And even the 6 over 4, maybe you're just going to write immediately that that's 3 halves, or I can think about that 6 as 3 times 2 and the 4 as 2 times 2 to get another 1 out. And 3 halves is going to be that fraction in lowest terms. Oh, I mentioned this in office hours yesterday. Oh yeah, question in the back. Yeah, for sure. So breaking all of our fractions down into that prime factorization first, that's really why we're able to reduce fractions to lowest terms. Yeah. Oh, I mentioned this to at least one person in office hours yesterday, but being really practiced with your addition and multiplication facts is really helpful for a lot of algebra things. And so if it's been a minute, I'm going to put some just basic practice sheets up in Canvas around addition and multiplication facts so that you can practice your speed with them. I will also mention that this is actually what I do when I have some insomnia issues. And one of the things that I do is I have, oh, you can't really see that. Okay. I have this version of Sudoku where, I don't know if anyone plays Sudoku, but I have this version of Sudoku where all of the boxes, not only does it follow the regular Sudoku rules, but all of the boxes, like you can kind of see that there's this rectangular outline and a little 12. That means in addition to all the regular rules, the sum of the two numbers has to be 12. Anyway, I am so fast with my addition facts because of playing this game. So, you know, there are ways to practice your mathy skills, but it really does help to get faster. So 12 over 144, back to actually doing some math. 144 is 12 squared. So the bottom here says 12 times 12. And that 12 over 12 is equal to a 1. And this gets back to that reason that I choose, instead of sort of canceling things, I choose to find a 1 because that helps me remember that this is going to be 1/12, not 12, not nothing over 12, but it's going to be 1/12. I will give everybody a minute to try D on your own. You don't have to do it by factoring the 180 first, but that's personally how I would do it. And if you're hanging out on Zoom with me, you can always put your final answer in the chat. I've got a couple answers coming in on Zoom. Still see people writing in the room. Let's mess with this one together. There are lots of correct paths through this problem. I am going to take what I think is the easiest path numbers wise. So when I look at 180, I know there are a bunch of factors, but for sure that 0 on the end tells me that is 18 times 10. And I'm going to go ahead and break that 10 into a 5 times 2, in particular because I know that my denominator has a 5. So now I've captured a 1. Now I still have choices, but that 18, that I can now break into 6 times 3. And then on the bottom, that 12, I can break into a 6 times 2. And that's going to give me 2 more of those 1s. So my final answer that I get is 3. And I know that I mentioned this before, but we're really a non-calculator campus for calculus, which means all of these numbers here, in terms of simplifying those fractions, these are all reasonable asks to do without a calculator. And so just to help give you context of like the size of numbers, the type of problems that you might have to do in terms of like just numerical things. On this next one, I've got 2 squared times 4. Now I could multiply that out and say that's 2 times 2 and get a 4. That's totally fine. Maybe I'll do that. So I could say that's 4 times 4. 32 is 4 times 8. So I know that that 4 over 4 is going to give me a 1. And then I can break that 8 down further to say that that's 4 times 2. So my 4 over 4 gives me a 1, and my final answer is 1/2. Again, if you can do that faster in your head, by all means, just do it and write a final answer down. 3 times 7 over 15. I'm going to take a look at that 15, break that apart into a 3 times 5. So that my 3 over 3 becomes a 1. And I end up with 7/5. Now, just as a quick check, I can't break that down any further because 7 and 5 are both prime. There is no there is no factor other than that number and 1. looking at G, there's not a ton I can do with this. That 4 is the only piece that hasn't been factored. So I can rewrite that as 2 times 3 and 2 times 2 times 5. So the 2 over 2 becomes a 1. Now, when we report this in lowest terms, if we've canceled all of the factors out, but I still have some multiplication going on, then to write this in lowest terms, I would write this as 3 times 10. So even though we factored it to get to this point, we really should combine all the numbers back together once we've made any cancellations that we can. $150 over $250. One of the things that I will just point out here, when we have zeros at the ends, I know that that means both of these are divisible by 10. Now, I'm about to write something, but don't read too much into it math-wise. 0 over 0 is not equal to 1, folks. But if I were looking at this problem, I really would just do that. Now, technically, math-wise, what I'm doing, but being lazy about writing it, is I'm really saying, well, that's 15 times 10 over 25 times 10, and that would give me a 1. But if you've got zeros on the ends of all your numbers, as long as you're crossing out the same number of zeros on the top and the bottom, technically what you're doing is dividing the top and the bottom both by 10, or factoring that 10 out. So 15 over 25, both of those are divisible by 5. So that's 5 times 3 over 5 times 5. I got my 1s, and I get to 3/5. Pausing for a second there in case any questions are showing up. We would just leave it as 3/5. So it is also equivalent to 30 over 50, but if the goal is to put it in lowest terms, that's our lowest terms answer. Yeah, but it would be numerically equivalent if you had the zeros there. Other questions? Good. So this all has like lots of words and parentheses and stuff. So I'm going to kind of cover some of that up for a moment, because really I just want to focus for a second on the problem at hand over here. So far, all the things that we were dealing with were expressions, not equations. The only thing that's different between an expression, a mathematical expression, and a mathematical equation is literally that equal sign right there. And the moment there's an equal sign in the problem, something magical happens for us with fractions. We can get rid of them. So if I have an equal sign in the problem, then I have the choice to multiply everything that's on the left-hand side of that equal sign and everything that's on the right-hand side of that equal sign by the common denominator, and all of my fractions are going to go away. It is not the only way to get through these problems, but if you are someone who isn't fast with fractions, or I'm not even joking, I really think people have a part of their brain that for some folks, when you see fractions, it's like there's a part of your brain that goes into like panic defensive mode, and you just start throwing math at it. right? It's like there's an invader, there's fractions. I'm just going to throw math at it, whether it's productive or not. If you are that kind of a person, that equal sign is your best friend. That equal sign means I'm getting rid of fractions. So I just want to do a few examples here to practice what I mean by that, the getting rid of the fractions. So when I look at this problem, I have two denominators here. I've got a 2 and a 4. In terms of common denominators, I could use 8, but I'm going to use 4. So if I multiply the whole thing through by 4, then I'm going to take everything on the left-hand side, and notice I put it in parentheses, taking everything on the left-hand side and multiplying by 4, and everything on the right-hand side and multiplying by 4. I'm going to do this next step sort of in slow motion, but it's totally fine. Again, if you can work through some of those steps in your head and not need to write out each step, that's totally acceptable. Well, on the right-hand side, more conventionally, we would write this as 4x and put the number in front. On the left-hand side, because I have addition inside of those parentheses, it's important to distribute the 4 through. So I'm distributing the 4 to the first piece and distributing it to the second piece. My entire objective is to get rid of the fractions. So when I distribute that 4 to the first piece, that x plus 1 over 2, I'm really going to pause for a second and think about it like this. The reason is, rather, if I were to distribute the 4 to the x and the 1 right now, I would have lost the fact that the whole point of multiplying by the 4 was to get rid of the fraction. I'm instead going to look at that 4 over 2 piece and reduce that first. So 4 divided by 2 is 2. So this turns into 2 times x plus 1. Over here, my 4s become a 1. So I've got plus 3 is equal to 4x. And I will give you all just, I don't know, like 30 seconds to finish that off, a minute to finish that off, come up with a value for x. I'm gonna take it slow, but I probably won't do all of these this slowly. I'm just gonna do this first example of this slowly. So we had 2 times x plus 1 plus 3 is equal to 4x. So first of all, this is a linear equation. It's an equation because of the equal sign, and it's linear because our variable x is only ever raised to the first power in the problem. My objective is to get all of the x's on one side and all the numbers on the other side of the equal sign. It doesn't matter which side I put things on. But the first thing I'm going to do is distribute this out. So I'll have 2x plus 2 plus 3 is equal to 4x. I'm going to first combine my numbers over here so that I end up with 2x plus 5 is equal to 4x. And then I'm gonna make a choice that might make some of you uncomfortable, but the choice I'm gonna make, personally, I'm always gonna move the x's to the side where the coefficient on x will become positive. So I would choose to subtract 2x from both sides, so that I have 5 is equal to 2x. Sorry. So that I've got 5 is equal to 2x and x is equal to 5/2. I like to avoid minus signs whenever I can, and often one trick to avoid minus signs is to just get comfortable with your variable ending up on the right-hand side of the equal sign instead of the left. Questions about that before I move on? Okay. So taking a look at the next one, I've got denominators of 5, 4, and 10. We have options for what to choose as a common denominator. Anyone want to throw out one possible common denominator we can use? Oh, question or answer? Answer, sweet. What were you going to pick? 20 works for me. If you didn't immediately see the 20 was going to work, other things will work too. 40 would work. But yeah, I think 20 is certainly a good choice. So with that common denominator of 20, I'm going to run through this one a little bit faster this time. So when I take the 20 and I distribute it into this first piece, 20 divided by 5 is going to leave me with 4. So I'm just going to write this as 4 times 2x plus 1. When I distribute the 20 into the second piece, the 20 divided by 4, it's going to leave me with 5. So I'll have 5 times 3. Distributing in here, 20 divided by 10 is 2. So that's a 2x. And 20 times 3 is 60. Now that we got it that far, I will give you a minute to get to solve that, to make it say x equals something. Should I do this quickly or should I do this step by step? I am okay either way. So how many people would like to see it step by step? Okay, let's do that. I don't think I have enough space on there to do it step by step. So I'm going to recopy this. 4 times 2x plus 1. Yep, I'm mumbling to myself. It's okay. 2x plus 60. One thing just to be careful about. Number one place where things go wrong is recopying the problem onto your paper. So someone check me. We do okay? So I'm going to start by dealing with those parentheses, and that's going to mean distributing numbers in. So 4 times 2x, I've got an 8x. 4 times 1, that's plus 4. 5 times 3, that'll be 15. And then I still have that 2x plus 60 over here. I'm going to go ahead and combine the numbers that I have. So on the left-hand side, I can call that 8x plus 19 is equal to 2x plus 60. This is the point where I would pause for a second and say which side has more x's on it. I'm going to move everything to the side with more x's so that my final coefficient works out to be a positive number. I'm going to subtract 2x from both sides. So now I've got 6x plus 19 is equal to 60. And then I've got 6x is equal to 60 minus 19. I'm going to let you in on a secret. Yeah, there's some algorithm for subtraction and you line stuff up and you borrow 10 from something and you keep track of garbage. That's actually not how mathematicians deal with numbers. If I look at 60 minus 19, what I'm actually going to do in my head is 60 minus 20 and then add 1 back. It is totally fine if you want to follow the subtraction algorithm and line stuff up and borrow something, totally fine. But really, I would say 60 minus 19, well, 60 minus 20 is 40, but I actually only subtracted 19, so that's 41. Which means x is going to be 41 over 6. And that's where we're going to leave it. 41 isn't going to break down into something where I might need to reduce that to lowest terms. So that's just my final answer. Now there's a good question in the Zoom chat about just can we practice some common denominator stuff? And like, how do you find the common denominator to use? So the truth is that usually there are lots of correct choices for a common denominator, but let's just talk through some strategies for dealing with it. So I'm not going to worry about what my numerators are. If I had some stuff over 3 plus some stuff over 5, plus some stuff over 10. One option for finding the common denominator that will always work to find the lowest common denominator is to take all of your denominators and do the prime factorization, meaning break them up into the smallest parts they can be broken up into. So I've got 3, 5, and that 10 would be 5 times 2. So then to get the lowest common denominator, I need to take every factor exactly once. So my lowest common denominator, I need a 3 and I need a 5, but because I've already taken a 5, I don't need another 5, but I do need the 2. So 3 times 5 times 2, or 30, would be my lowest common denominator. Yeah. Oh yeah, for sure. We will definitely get more practice with the distributing part. Yeah. Let me do one more, just finding a common denominator. So let's say I had some stuff over 12 plus some stuff over 15 plus some stuff over 24. This is kind of garbage. This is pretty bad, but I just picked some numbers. So if I were looking for a common denominator here, I fear it's going to be pretty big. But here's what I would have to do. I'm going to break each of these up into their prime factorization. So 12 is 2 times 2 times 3. 15 is 3 times 5. And 24, well, I can't do this quite in my head, but that's 6 times 4. So that must be 3 times 2 times 2 times 2. So if I were finding the common denominator here, I'm just going to go through and start grabbing the pieces. So I need a 2 times a 2 times a 3. So I need a 2 times a 2 times a 3. So that took care of everything here. I've already taken care of the 3 now, and a 3 and a 2 and a 2. But I still need a 5 and also another 2. And then I could multiply those back together. So that's 10. And 2 times 2, that's 4 times 3, that's 12. So my common denominator here would be 120. One of the things that makes some people look like they're good at math is that they're fast with numbers in their head. And that looks and feels like good with math. But that doesn't actually necessarily mean that if you aren't fast with numbers in your head, that you aren't also good at math. But I think this is one of those more tangible things that makes it feel like the person next to you is good at math, right? So if someone is fast at finding common denominators, somewhere in their head, their brain did this, whether they realized that's what was happening or not. And if you need to write it out on paper, that's fine. Not everybody's brain works the same way. Okay, back to, oh yeah. Like this one? So this 5 is kind of like already taken care of. So when we actually go to find the common denominator here, right? I know that 10, hold on, let me just write this bigger. What I have 3, 5, and 10. Okay. So stuff over 3, stuff over 5, stuff over 10. Well, the objective when we find the common denominator, like finding it is part 1, but then we're actually going to have to do something with it. So if I were getting a common denominator here, then I need to take each of these pieces and make them all have the same denominator. This one is missing that 3. This one is missing that 2 and that 3. And this one is missing a 5 and a 2. We absolutely could take that other 5 as well, but it would not be our lowest common denominator because we already have everything with the same denominator right now. So if you take the additional 5, it's not wrong. It just means that you would end up multiplying every single term by 5/5. And I don't need to multiply every term by 5/5 again, but it's fine if you do, right? It's just a matter of, that's like the difference between talking about the lowest common denominator versus just any common denominator. They'll both work. I just choose to make numbers smaller whenever I can. I'm moving slowly, checking for questions in the chat. So let's take a look at this next one here. And step out of the way. So if I look at C, I've written the fractions differently this time than I did on the previous problem. I've made those fractions physically smaller rather than having a big ratio kind of fraction. But my only denominators here are 4 and 2. So again, I would choose a common denominator of 4, but it's fine to choose a common denominator of 8. So I'm going to multiply both sides by 4. And visually, I think this one is a little bit messy, right? I've got parentheses inside of parentheses. There's all kinds of stuff visually cluttering this problem. We have a choice to make. But if the objective is to, as quickly as possible, get rid of the fractions so that your brain has space to think again, then I'm going to look at these bigger parentheses. And there are 2 pieces that are separated by subtraction. So when I go to distribute the 4, I'm going to distribute the 4 into this first piece and the second piece that are separated by the subtraction. When I multiply the 4 to that first piece, what I end up with is 4 times 3/4 times x plus 1. And when I multiply it into the second piece, I end up with 4 times 3/2 times x. Now the objective is to get rid of the fractions, which means I'm now going to look at that 4/4 and say that's 1. So I've got 3 times x plus 1. And I'm going to look at this. We talked a little bit about this on Monday, but that 4, if it helps you to see that as 4 divided by 1, to make sure that you're seeing that that 4 is in the numerator, not the denominator. But that 4 is in the numerator, so 4 divided by 2 would leave me with a 2. So I've got 2 times 3x is equal to 20. Now I know there was a question about the distributing things, and I don't know whether that example was helpful or whether we actually should go back to the previous example. We're good? Okay. I'm going to pause for a second just to, like, you all can solve for x on your own time if you want to, but I want to pause for a second to point out something that comes up a lot. A question that I get a lot. So I don't know if this is going to be a great example of it. but tempting to do this. The question that I get / mistake that I see is to think about distributing the 5 to the 3 and then also to the x and the 2. Now, numerically, what you're doing, if you distribute it to both the 3 and also the x and the 2, so you're actually multiplying by 25, not by 5. Because there's already multiplication here between the 3 and what's in parentheses. So this, when we talk about distributing into some parentheses, we're really looking for either addition or subtraction as kind of that break point that has split the stuff in parentheses into different parts. And when we're distributing things, we're distributing to either side of those breaking points. So here, we're not going to distribute to the x and the 2. This is just going to become 5 times 3 times x plus 2, and then minus 5 times 7. Just wanted to pause to point that out, because I think sometimes this kind of visually interferes with the whole idea of multiplying through to get rid of fractions, because I think those parentheses kind of visually interfere with our lives. Let's go ahead and finish off D and E here. I think we got time. So if I look at D, I've got a 4, a 7, and a 2. So if I were going to find the common denominator, the 4 is 2 times 2. So I for sure need two 2's and a 7, but 2 2's and a 7 will take care of that 2 over there. So 4 times 7, that's 28. So I would multiply both sides by 28. And then I'm distributing that 28. So again, this part in parentheses, the place where it's breaking up is right here at the plus. So I've got one piece and another piece. And on the right-hand side, it's that subtraction that's breaking that up. So I have one piece and another piece. So this time both sides have to get distributed. So I'd have 28 times x plus 0.5 minus y, whole thing over 4 plus, well, 28 times 1 is 28. Over here on the right-hand side, when I multiply in, I'll have 28 times y over 7 minus 28 times 1/2. And if we simplify all these fractions, the 28 divided by 4 is going to leave me with 7. 28 over 7 is going to leave me with 4. And 28 over 2 is going to leave me with 14. So I didn't leave myself nearly enough space to write here, but I've got 7 times x plus 0.5 minus a y plus 28 is equal to 4y minus 14. Technically, my instructions for the worksheet were not to actually solve anything. And here I have both x's and y's in the mix. So I would have to give you more instruction if I wanted you to isolate the x by itself or isolate the y by itself. But for now, I just wanted to practice the getting rid of the fractions part. Very last problem. in terms of a common denominator, there's only one fraction in there, so our common denominator is 2. And I am going to let you all have a moment to practice distributing the 2 out to both sides, because I gave us one with messy parentheses.